Welcome back to ECE 320A. This video is entitled Maximum Power Transfer, and it's coming to us from Chapter 10, which is the single-phase sinusoidal steady-state power chapter. And at the end of this unit, which we're in Unit 2, as homework number 2 is due, and exam number 1, which will cover material from Units 1 and Unit 2, is also going to happen after completing Unit number 2. Today, what I want to talk about is the relationship between the impedance of the source, which we're calling Z Thevenin, and the impedance of the load. And in this particular segment, what we're learning or will state is that to transfer the maximum amount of power between the source and the load, we need the load to look like the complex conjugate of the source's impedance. Again, we're dealing with sinusoidal steady state conditions, and we want to know what's going to allow us to transfer the maximum amount of power from the source to the load. And as I just said, the maximum power will be transferred from the source to the load when the load impedance, which I'm denoting as capital Z sub capital L, equals the complex conjugate of the source impedance, capital Z sub capital TH. So if you have the ability to adjust the load impedance, and if you know what the source impedance is, then to transfer the maximum amount of power from the source to the load, you would want to select that load impedance to be equal to the complex conjugate of the source's impedance. Here's the diagram that represents that, and you can then hopefully see the two different pieces to this. We have our source piece, which we now have a Thevenin equivalent representing that. We have the source voltage as a phasor, and we have the impedance of the source. And here is really the connection between the source and the load. And we have identified then the impedance of the source as Z Thevenin. And here is the second piece of that part, or of the circuit, and that's dealing with the load. And in order to get the most power to the load, we would select the load impedance to be the complex conjugate of the source. And this is useful if we were dealing with communications, if we're trying to transfer the maximum amount of power over the airwaves, or if we're trying to build a sensor that's as efficient as possible, then this concept is very important. But in fact, in a power setting, this really isn't what we want. The load impedance, we really don't want to be looking like the source, because we're trying to move a large amount of power. And so we really want the source impedance to be very, very small relative to the end or the load side, and we want to be able to transfer as much power as we can, or when we're moving large blocks, it's not so much that we're trying to optimize or maximize the power, we're trying to push as much power as we can to the load side. And the reason that we don't really like this maximum power condition in a power setting is because we don't want half of our power consumed on the source side. In fact, we want to push a lot of power fractionally to the load, and hopefully our source will not be consuming that much power. And if you want more information on this, I would suggest you look at section 6 in chapter 10 of the textbook.